In this recording, we begin our discussion of grid-connected PV systems that also include batteries. Let's start by going over the goals of a residential or commercial scale grid-connected PV system with batteries. The key goal of any grid-connected PV system of these types is for the local loads to be able to run on solar electricity when it is available, and grid electricity otherwise. It is the same goal for a grid-connected PV system with or without batteries. In both cases, we want both the PV system and the grid to be connected to our loads at the same time. This way, the grid can contribute electric power to the loads whenever they need more than the PV system is producing. This includes in the daytime, whenever the PV system cannot produce as much electric power as the load needs, and at night, when all of the power for the loads needs to come from the grid. The point is that whatever power the loads want, they can get from either the PV system or the grid. In addition, we connect the PV system to the grid so that whenever the PV system generates more power than is locally needed, the additional electricity can be sold onto the grid. This can offset some or all of the electricity drawn from the grid at high load times or at night. The PV system may even be large enough to generate more electricity than the loads use overall during some extended period of time. Another goal for a PV system of this scale with batteries is to provide electricity if power ceases to be available from the grid. This is a goal for any backup electric power system, with or without PV. Causes for a loss of grid electricity include equipment failure caused by weather, aging, or overloading, precautionary outages, and grid disturbances that may be hundreds of miles away. Backup power systems for grid outages are found in many sizes and usually do not include PV. Computers may have small uninterruptible power supplies using batteries and sometimes also a fuel cell. Hospitals and other critical facilities have backup fuel power generators and use batteries to provide power during the short interval from an outage until the generators turn on. But the unique goal of a residential or commercial scale grid connected PV system with batteries is for the PV array to provide some or all of the electricity needed by the loads during a grid outage until grid power is restored. This is the feature that distinguishes such a system from a grid-connected system without batteries, and from a common backup electric power system. A grid-connected PV system without batteries is designed to turn off when grid power is lost, and only begins working again after grid power is restored. A fuel-powered emergency generator is limited by the amount of fuel that is stored locally or can be brought in during a grid outage. Natural and man-made disasters that cause grid outages may also impede fuel deliveries, and there may be many competing destinations for the fuel that gets through. So one reason for a residential or commercial scale grid-connected PV system with batteries is to extend the time emergency power is available. With PV, electricity can be available beyond what is stored in batteries at the time of a grid failure. Also, if a fuel-based generator is available, PV can extend the time electricity can be provided with the available fuel. As such, PV can reduce the batteries or fuel needed to provide power for a particular grid outage duration and avoid some costs for obtaining, transporting, and storing fuel. Whether these advantages are worth the cost of including PV in an emergency electric power system depends on the situation. Grid-connected PV systems with batteries can be divided into two broad groups, which are called DC-coupled and AC-coupled. These terms should not be confused with the concepts that have the same names in the fields of communications and sensors. Of the two types of systems, DC-coupled systems are older and more established. In addition to many existing systems, DC coupling is used in many new systems that are being installed. AC coupling is hardly new, but it has been receiving a lot of interest recently. New equipment and approaches are being developed by several manufacturers, and there is as yet no certainty about the optimal design. To quote Solar Pro magazine, AC coupling is still the Wild West of renewable energy applications. We will discuss some of the reasons for the recent interest in AC coupled systems. All grid-connected PV systems with batteries, whether DC coupled or AC coupled, have a general design that looks like this. The systems have a DC side and an AC side. On the DC side, we find the PV array and the batteries, and on the AC side, we have the connection to the electric utility grid, and almost always some AC loads. It is the connections between these components that are different in a DC coupled system and an AC coupled system. Let's look a little at the box in the middle. In a DC coupled system, the PV array and the batteries are connected to each other through a DC bus, as shown here. In all systems, we need a charge controller to disconnect the PV array when the batteries are fully charged to prevent overcharging. Often, the charge controller will include a maximum power point tracker. This optimizes the power flow from the array to the DC bus. The DC bus is connected to the grid and the AC loads through an inverter and charger. In some systems, there are also DC loads that are connected to the DC bus. By contrast, an AC coupled system looks like this. The PV array and the batteries have their own inverters, and then they are connected to each other on an AC bus. We'll add some more details to this when we discuss it further. To our knowledge, there is no company that presently manufactures a single product containing all of the units in the middle box. Rather, systems are pieced together for a particular project from products that are on the market. Usually, the inverter is an inverter that is also used in grid-connected PV systems without batteries, and the maximum power point tracker is built into it as shown here. Comparing the two systems, we can see the main differences. In the DC coupled system, the PV array and the batteries are connected through the DC bus, and single inverter connects the DC bus to the grid and the AC loads. By contrast, in the AC coupled system, the PV array and the batteries each have their own inverter, and then the grid, and the AC loads are all connected through the AC bus.